Yeah. Hello. My name is Gerard, as you can see here, and I come from Spain. And I'm going to give a presentation about this topic. And I put it in chronological order. So I'm going to start with my past work, the actual experiment I'm doing now, and what I want to do next. I've never done a presentation so long, so I hope I put a lot of videos. So it's going to be, if you are bored of listening to me, you can just watch the video. Some of them are better than others. So yeah.
You allow for questions in between?
Yes, I'm actually recording this for myself, so I can later watch the video and say, oh, this person asked me this, I didn't get it at the moment, but maybe later I can think about it. I don't have notes, so feel free to ask questions, even if they are recorded. And maybe if I like the presentation, I will upload it online. And then if you don't want to be in it, you just come after to me and say, can you remove my voice, please, when I ask the question? Okay? So basically, I started working in 2013 in Barcelona in the Interactive Technologies group. It's a group of computer graphics. And when I came there, they were working on cinema projects. But I did something a bit different. It was basically the start of the virtual reality of these goggles that came out, and we just had one of the first models, and we tried it, and I got really dizzy. So they gave me a bit of free space to do my research. So I decided to find out why are we getting sick with these goggles, which they are already theories, but I wanted to develop a system that you could get less sick. So basically. Well, there's another talk on internet that I explain this, but I'm gonna basically show what I did on a video. So basically I used the inertial measurement unit of the head-mounted display of the Oculus Rift, and I double integrated the acceleration of the accelerometer to get the position. And it's not a very stable system. You can only do one step at a time. Because the drift on the double integration of the acceleration, if somebody tried this before, you will see that there's exponential. And basically, I did an experiment where the people had to move with my system, and the people had to move with a game controller, which is what usually people use in video gaming. No? And I compared how people was getting sick on a 15-minute immersion. These are environments. I made them according to another PhD that did some locomotion tasks. So basically, there are some. The first one was adaptation. It was the Museum of the Louvre, and these ones are like going back and forth, going through some corridors. And the results were quite interesting, because with this system, even if it's not 100% accurate, the people got half sick, and also I got to see how far can you get with this? There were people that when they were using the game controller, they got really sick, they were sweating, they were white. They reported me the next day that they felt sick all day just from 12 minutes immersion. So it's a device that's very immersive, but it's very, you have to take into account that people can get really sick. And also there's no predictor on this. There's work from Kennedy that he did experiments with 1,000 users, and they couldn't predict why people would get sick if they were using goggles or like surrounding screens. So there's also a lot of research by the military, because they wanted to do simulators for people to train them on airplanes or other kind of simulations. And there's reports from the 80s and the 70s with a lot of people, and they don't find out why do you get sick or why don't you not get sick. So I had people that they didn't get sick at all, and I had other people that got really, really sick. So basically, these are the results. Explained really fast. With the game controller, they got double as sick as with the position estimation system. There was a lot of variability. I had subjects that didn't get sick at all, and subjects that abandoned the experiment. They said, I don't want to continue. Luckily, I didn't have anybody that dropped out from my system, but well, there are 2 conference publications out of this. And then we entered a new project that was for interactive virtual characters and for medical applications. So basically, you would have maybe a companion that, if you're an elderly, you will have a companion that would ask you, how is your day today? how are you feeling? This project, there were a lot of universities, a lot of partners from all over Europe, and our side was to make the 3D virtual character on the web. So I made a video for a conference in August, and I'm gonna just play it. There's some music on the background. Please don't judge me by this video. I made it really fast. I was coming from holidays, and I just found out the first Creative Commons song, and then I put it up, and I made the video really fast. So I hope it's not too much. Wait. No. Okay. It's looking promising.
Is something troubling you?
I have a headache.
Can you elaborate on that?
My heart hurts.
Is it important to you that your heart hurts?
Yes, indeed. It is very important.
You seem to be quite positive.
I like to be positive.
You say you like to be positive.
It is always good.
Really, always?
Where are you from?
What if I were from?
Then you would exist.
You're not really talking about me, are you?
For the next part of the video, I'm going to show the components created in WebGL Studio to support the embodied conversational agent. The VML Realizer library controls the virtual character. It can receive messages from the inside of the application, but also through post messages. This VML Realizer is used in the project Christina and was also successfully connected to the engine Greta. The facial expression system uses valence and arousal to generate expressions. This two-dimensional space can be defined manually to generate new expressions. The speech-driven lip-syncing works in real time with the web application.
The juice of lemons makes fine punch. The juice of lemons makes fine punch. The juice of the birch canoes fit on the smooth planks. The birch canoes fit on the smooth planks. The birch canoes fit on these days. A chicken leg is a rare dish. These days.
Aside from that, WebGL Studio has many tools to configure the scene.
Okay, so basically there were a couple of publications that came out, the web-based lip sync, and also this was accepted as a poster in the conference in August about this interactive agent that you could speak. The artificial intelligence was from the 60s, so you wouldn't expect too much from speaking with the system, but it's just a proof of concept of the power of the web, and we did it in our department. Probably you didn't notice very much the lip syncing on the first video when you were speaking with the agent, and you would notice it much more with the video that you just look at the lip sync. Anyway, so some of the things that came out, and basically I was hired here in 2015 to work remotely and to help out with all the visual part. And basically it was a technology transfer from the work that I was doing in Pompeu Fabra, and I was applying it here. So basically the first thing, well, I was hired to do like virtual reality with a head-mounted display, but then I was switched to do some of the environments. And probably you've seen some of them. You might have seen the cafeteria that's in the entrance. Well, it's the cafeteria from Oldenburg. I just basically took a bunch of pictures, and then I from Spain, I just modeled a part of it. So it's not exact. When I was coming back to Oldenburg, I was like, oh no, this was not like I made in my model. And then there's also NeSSy, but I think we are not using this environment, so I don't know. I just made it going through the gesture. So I think later I'm going to the office where we are. Yeah, so basically I will be here giving the presentation. Nobody. I put this, I liked it. And then my latest work was the train station from Oldenburg that it's now being changed, so I'm not very happy that they're changing the model.
People from Oldenburg love it because they know, okay, this is what the train station was used to be.
Yeah, old school train station. Okay, so with these environments, it's cool because you can move the trains and you can control things. Basically, I don't have a video, but all the virtual characters, I also put them here, and you can have interactive environments. And also, I was helping out with the experiment for Marge and Gizo. Basically, it was a very big experiment with lots of results. And basically, one of the points was to check out the effects of the lip sync and the effects of looking at the target speaker. And there were several conditions. They had to follow conversation, and also the coordinate measure response. So they have to check out 4 persons are speaking at the same time, and you have to find a keyword and recognize a color and a number. And well, the results were that, well, not exactly like this, but you could say that the lip syncing and the gaze to target was the condition that was closer to the video, and that people liked more and perceived that it was easier. So in the present, I'm hired, I'm with this European training network. We are 14 PhD students in different institutions. There's Groningen, in Nijmegen, UCL, the Basque Country, University of Crete. And I'm hired through Horse Centrum, but I'm also collaborating with the university. So what's the problem? What I'm trying to solve in my PhD? Basically, it's very different when you are in a lab with a bunch of speakers, or when you're in like the real train station. Your behavior, the cues that you have are very different. So with the pilots that we did, also in the March's study, you can see that the head motion is very different. Well, for example, for speakers, you don't see them, you can see them, and your head behavior will be very different. So this is actually very relevant for hearing aids, because they sometimes have beamformers, and it's very important when you're looking. So now all the hearing aid testing is done without visual cues that will change your head behavior, and then the results will be very different from real life. And this is something that the hearing impaired people complain about, that they go to the lab, they put some noises, and then they go on the street and it's not the same. They say, okay, in the lab this works perfectly, but I go on the street and it doesn't work. So basically we want to move to more like real life experiments or ecological, and there's some people that is just putting a bunch of sensors to people and putting them on a real life situation and then trying to measure out of it, something out of it, which is difficult because it depends on intersocial interactions. There's a lot of variability. And the other people that are doing lab experiments, they are also using these people that are using virtual characters with this kind of setup for speakers, and some also real life situations, and they are doing like speech intelligibility and listening effort, but not so much on the head behavior. That is what I'm trying to solve. So what do we have in Oldenburg? We have this gesture lab. It's over there. You can always come and check it out. We always have cool demos. Yeah, actually, yeah. I'm actually looking for subjects, so it's very fun. I can maybe later you can play with the archery game. So basically, we have the cafeteria, for example. Also, we have a street and other simulations. There's actually experiments that have already been done with the street from Richard, and Marge is preparing some with the cafeteria and other environments. So what am I doing? Basically, my idea is to compare a system like that one that we have with a 2D screen with a head-mounted display. And why? Why am I doing this? So basically, this is very expensive. This is very difficult to configure, and it's very difficult to reproduce. Obviously, if you have a 2D screen that is like a different distance, or the projector is different, the warping function is different, and this is very easy. Basically, it doesn't take a lot of time to configure, and you just need a PC and the goggles, and you can do it everywhere. So for people that have a research facility with a loudspeaker array system, and they want to test hearing impaireds, and they think, yes, I'm going to put a 2D screen. Okay, so hire a guy and spend 1 year doing it, or less, But with this, it's much easier. You can download it from the internet. You can have a simulation. Obviously, you have to design the space. If you want to have virtual characters, if you want to have a train station, you have to do that. But there are many tools for this because it's consumer use. This is not consumer use. This is consumer use. Everybody's trying to do this. But it's not validated. So what I'm trying to see is how people behave in this situation and in this situation. So basically here you would have a much broader field of view. We have like around 180, and with this one you have a much narrower field of view. So you will behave differently. And also you will behave differently if you have visual cues or you have only a loudspeaker array. And also it's dangerous. As I showed before in the other experiment, there were people that got really sick in 10 minutes. And also this screen is also dangerous. I think Richard commented that there were some people that refused to look at the screen on a street simulation that they were walking through. So it's not something you can say, yeah, I'm going to just put the simulation on the street and make the people go through it, because you might get people that get sick and refuse to look at the screen and to do the experiment anymore. So just watch out with displacements on with visual simulations. So I'm going to just show a video, funny video of this is one of the first demos that came out for free. That was a roller coaster. Okay. Okay. It's better if you do it seated down. Yeah, there's a moment also that the train track ends and you just make a jump with and the guy just goes on the floor. Okay. So I'm going to show a video of my experiment. There's no audio, but it's so you get an idea of. It's very simple. I'm basically having some conversations that we recorded from a video, from virtual characters, and with audio only. And then I'm comparing the 2D screen and the head-mounted display. So like you have this with the cylindrical screen, the same thing with the virtual characters on the cylindrical screen. And then here you would have the same thing with the head-mounted display. So I designed the same room so it would be more or less similar. And the environment that you're in, you can also see the chair that you're sitting in and the exit door. And here you can see the visual characters. This is quite different because in this case, you're seeing something in 3D. Okay, it's different from a flat screen that you're looking at it. And actually you can project objects that are closer from the distance of the screen. So you can have objects that are this close and you feel that they are this close. So for my pilots, there are only 4 people. I made some drawings here. Well, maybe it's not so clear to see, but when they are grayed out, it's audio only, and when they are not, it's with visual conditions. Here you can see the small goggles on the top part, and they are not wearing goggles, and this is the target speaker. So basically, the main result, that is what I was expecting, is that with the head-mounted display, people move more the head towards the target speakers because they have a narrower field of view, so they are forced to look more at there. But they look in a similar way when they don't have any visual cues with the glasses and the 2D screen.
Yeah. More about the characters. I didn't quite get that. So you don't want to simulate the real person, but some similarity is somehow intended also.
Yeah.
But they look always a little bit like criminals. Intentionally?
No. Actually, they are supposed to be a representation of. I don't know if the guys that were recorded in the video. I don't know if they are criminals. I don't know them very much. So they are supposed to be a representation.
But they are virtual counterparts. Daniel, he's a real criminal.
The thing is that they don't have facial expressions, so they are very serious all the time. We didn't include facial expressions because when you start to go into emotions, it's a completely different field, and it might evoke things to people that you don't want to. The best idea would be to have these videos here, and have some computer vision that tracks every facial feature of the person, and then you can map it on the virtual characters, and you have a 100% reproduction. But this is not what we're aiming for. We are aiming to very simple cues, lip sync, and gaze to target, and see what's happening. Is this enough? So other people can use it. Because having a computer vision system that tracks this, it's complex if you don't know how to use it, and you might have to hire some expertise, but to do the other part, at least it didn't take so long for us to make. So they are very simple cues, and we are trying to see if they are enough for the people to follow a conversation in a natural behavior.
So you say, if I now understand correct, that you can only make them look less criminal if you do some real life emotion.
If you make them a bit happy, they will look
more static. Static happiness.
Yeah. 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 You can make just the lips a bit up, and they will be happier. Yeah. In some I think in some environments we made it because we had like agents sitting on the background, and they were all very serious, and this is like make them a bit happier, and it looks more friendly, you know.
I show demos of it.
To say
yeah, that looks like
But it's important to know, because we already know, for example, that just the fact that the other characters in the scene turn their head increases the sense of reality and immersion. So that's it's not much that is needed. That's really interesting.
So one of the questions that I'm trying to ask then, apart from validating the technology, the head-mounted display, is if people wearing hearing aids, do they really want to use the goggles? Because it's very intrusive. It's something that you put on your head. It's heavy a bit, and you don't see anything else. It's a new technology, so maybe the elderly say, no, I don't want to use this. It's very uncomfortable. Maybe I got dizzy in another experiment. I don't want to do it. So it's a question that I want to find out if they maybe say, yes, wow, this is really close to real life. I'm really comfortable with this. I would like to do all my testing with these goggles. We'll see in the future. So also it's good to know some of the things that I'm doing wrong is that the lip syncing is not validated, and we used it in the other experiment and this next one. We don't know what the speech intelligibility increase that it adds. So it's something that I have to look for. Also, we are not using lumbar speech. The conversations were recorded in silence. So if you want to have a natural conversation on a noisy environment, it will be no lumbar speech. Also, there's some people in Denmark that are doing some, instead of, we had, for example, with a head-mounted display, we had 4 panels with video, but it would be even better if we had 360-degree videos with head-mounted display. Like everything is a video, and you're looking around, and all around you is a video. And also the 2D cylindrical screen is a bit far away from cave system, so you only have like 120 degree. So it would be best to have a complete surrounding and also ceiling on top. But well, the problem with the cave system is the audio is not so good because they have reflections because it's a square. Well, I'm not going to go into depth into explaining what's a cave system and this. So the future. What am I going to do next, or I'm planning? One of the main things is validating the lip sync with OLSA. Shouldn't be so difficult, so it's the next thing that I want to do. There's similar work done from Hartmut Meister. And we are now thinking, they just did audio only, speech intelligibility, and speech intelligibility with the virtual characters and lip sync. But we might have video recordings from the OLSA that we might record in the future. We don't know yet.
Maybe we should also discuss the way how we plan on doing this.
Okay, so the way that we plan to do the video recordings is to have one OLSA sentence played over and over, and one person repeating the same sentence until it's perfectly synchronized. It's not 100% valid, as the virtual characters are not 100% valid, but then we can see, we can have a reference of a video, simulated video, a reference of the virtual characters, and the audio-only condition. And then we can see, according to the literature of real videos, if the increase on speech intelligibility, is it reasonable or not with these video recordings.
Psychologists, they also do recordings. Jochen Rieger colleagues.
But we are in contact with.
I knew only about video recordings from Dienst. They also do something with speech. They also do something with speech.
So maybe you can ask, but I'm pretty sure they have CRM.
Okay.
But we can ask.
So next point, it's basically something that we spoke with Kirsten and Marcus. It's to test the hearing impaired with some realistic environments, maybe a cafeteria, train station, and then test them with goggles and the other thing, and ask maybe some open questions and some speech intelligibility tasks to see what would they prefer to use. The open future, so we have this technology in the lab, and there are many ideas, but I'm one PhD student doing one PhD, okay? So maybe it's always good to have a bit of a showing what also can be done in the lab. No? So for example, as I said before, these goggles, what they allow you to have is objects that are closer to you rather than on a screen, and they are on 3D, so it's a bit more immersive. So I'm showing a demo here of grabbing a sound source and moving it around me. Okay, it's a simple demo. If you want to come to the lab, it's easy to try. And it's actually, it feels quite natural when you put the sound next to your ear. So it looks like it's coming from your left ear because you have the array with ambisonics of loudspeakers behind.
The sound that you heard, is that connected to the sound that you produced in the video, or what was the sound simulated?
Yeah, the sound that you were hearing, this sound was played on the loudspeaker array, and I used the microphone that's on top to record this and make the video.
So this is really immersive, so you can check it. So the sound is generated, the video is generated in this video engine system, and then you have really a 3D view of this sphere being closer on left and right, and so on. You have really the 3D impression. And at the same time, when in parallel, the sphere generates a sound in the virtual environment, and it's rendered on the task.
So if you put it, now we only have like
simulate a sound emitting sphere. That was
yeah, sorry. And you basically, like, you have distance perception also by the volume, and on the azimuth plane perception, because we don't have the 3D audio system yet. It's only on the plane. So maybe it's a hot topic. There was a job opening on Oculus Research. Oculus is the ones that developed the goggles. And this was in April from this year, that they're looking for people looking on psychoacoustics with a head-mounted display. So if anybody wants to work on this, it's interesting. Then, well, this is just something that Marcus commented on, and I'm just going to show a demo of the train station. That I'm using the goggles, but I'm also playing it on the 2D screen, and you can see both. You can hear the audio and see more or less how the train is coming. So, okay. So you can see that it's a bit different, because in one case you can really look around you and see what's happening behind and on the sides, and in the other case you just have the 2D screen in front. So this is it's good to know that if you're using this screen and there's a sound coming from behind, the people will not look behind, but if you're using the goggles, they will look behind. And again, goggles are easy. Making a 360 circular projection is not easy. And also other things like engagement and motivation in interactive environments. If you have somebody replying to you, will you try to do the task more? Because we know that in listening tasks, sometimes the subject just refuses to keep going because it's very hard. So maybe you have an interactive environment, they try their best more, and also facial expressions and emotional speech, something interesting to check out because we have the emotions and we have the speech, and then we can do these Gordon experiments. So thanks. Yeah.
One question regarding emotion with facial expression. What is the model with the emotions to show the emotions, anger, fear, and fun, and so on? So you will think about different muscles in the face and so on to simulate emotions? Or?
So basically, there was a work from another PhD student on my department that they used the balance and arousal wheel, and then they validated with 400 people to see if they recognized the emotions that they were designing. So if they were making like happiness, anger, sad, depression, enthusiasm, and some others, and they got pretty good results from this. So basically, we have the balance and arousal model that you saw how you can make the expressions really fast, and then you know that if you use the model design, like the expressions that predefined from this PhD student, that they are valid. So this has already been validated that the emotions are corresponding to the modifications on the face.
Actually, we are planning on extending this collaboration with Barcelona groups exactly for facial expression, so that we can also include it maybe apply for some joint project, or so we would not do the research ourselves, but some collaboration, and that would allow us including basically validated facial expression stuff also in our exactly what we've been talking about before. That for the time being we lack facial expression, but of course for ecologically valid speech testing and audiovisual environment we need it, and then we would like to just take these validated values and apply it to collaboration. But this is, of course, we open now a very new world, and so we have to go step by step. So we see basically some endpoint, which is really tons of possibilities, and everybody's now looking forward to getting this to run. But now we can demonstrate it in the lab, but to really come to a final conclusion where we can apply it during impaired listeners in a standardized form, there's tons of steps to do, starting with very easy validation steps. So it seems so slow. It's frustrating because we can demonstrate everything, but how to really do standardized experiments which have been validated, that is many small frustrating steps which we are now about to take. So I'm afraid this will take time. So for example, what is now established in psychoacoustics and audiology, or the audio-only stuff, to develop and validate this so that in scientific community it is accepted. It took like 50 to 60 years. So we are planning on doing this now in maybe 10. Even less. 10 months. No. So expectations are very high, and we can already demonstrate tons of stuff so that people really get excited. And then they ask us for, what shall we do now? We don't know. Then we have to take the small scientific steps, which might be frustrating. So I'm afraid we have to take these steps. And say, okay, we even only validate lip sync, and there's no facial expression whatsoever. If you switch on everything at the same time, we have no chance of getting this validated. So this is why I have to ask for patience, and also we have to see that we have to do the small steps. But we have all this in mind and can demonstrate.
But connecting to that, for me it's not quite clear what is the real hypothesis or the real target then of your PhD thesis.
Okay, so basically we have this technology, that's the head-mounted display, and we have a need to include visual information in hearing impaired testing. Well, a supposed need, because I don't know, I haven't spoken with a lot of them, but I have the impression that they want to have visual cues when they are testing. And then we have a problem that's making visual cues possible in hearing testing facilities. And with the head-mounted display, it's very easy. And then if we validate this technology and people start using in different labs, then that hearing impaired testing will be different, will be very different from what's been since now, I think.
So that would mean you take basically all the possibilities you have now and come up with a solution, an intermediate solution at the end of the PhD that allows audiovisual testing of hearing devices in a number of conditions, in a validated way.
Yeah. Yeah, some of the things that we implemented, the lip syncing strategy that we're using now, I don't know, in JavaScript, 80 lines of code. It's not so much. And in C++, Kiso did it, I don't know, it's also not a lot of lines of code. So it's not something very complex for other persons to implement. And also the gaze tracking, it's also something very simple things that it's not that we're using a really complex computer graphics system. And I mean, movie companies spend 1 year to just make one person, you know. So we're making really simple stuff, visual stuff, with virtual characters to make it work and see if they work, if it's enough, no, for the people to use. Did I reply to your question, or still?
No, I still don't see the real target, so to say. What will you gain from being able to perform the experiment with virtual world,
okay,
so to say, and virtual audio in respect to lab tests?
That your head behavior will be very different. It will be very different if you're only using audio only, or if you're using visual cues. That was the main. The main point is that if you have only loudspeaker arrays, your head behavior will be very different if you have visual cues, and that's very important for hearing aids because they have direction and they are here. So if you change your direction, they will perceive the sound differently.
So one study could be, for example, you have this conversation in the cafeteria, and you just show that people behave differently if they have the video compared to no video, and then switching on a hearing aid will change behavior again. Because then people are forced to change behavior because of the functioning of the hearing aid. So that would be one study showing, okay, it is valuable to enrich audio. This is what it's called, enrich network. So enriching the audio presentation by visual cues. This has already been, the pilot data already showed this is required. And then showing if you switch on the state-of-the-art hearing aids, that these force you to change behavior. And that would be one very important step.
So the observable, the one that you will always look at, is head movements.
One of the things is head movements, and the other is comfort, because maybe people don't want to use this.
And speech perception.
Yeah.
And maybe also loudness perception. So I talked with Gerard that we can include it in the Cluster of Excellence project, a new one, where we want to compare real life situation, real life loudness perception, also with the screen and also with the VR glass to compare whether the loudness perception will change dependent from acoustic only and acoustics plus visual environment. Maybe it's also
yeah, it's about psychoacoustics also. Some psychoacoustics. If we can test them, I mean. Yeah.
That's again different.
No,
yeah.
It's again yet another study.
Yeah, the thing is that. Yeah, we have the system, we can test many things. It's one PhD, one thing.
That's why I asked you what is your.
Okay, yeah, my topic is, yeah.
Where do you want
yeah.
is the observability that you want to do, what is the scientific problem?
And this is what I was saying, okay, there's a scientific problem to solve. First requires very difficult steps. And frustrating and boring steps, for example, validating lip sync. That is a very boring step. You say, okay, why shall we do this right now? Because we could do this right now, which is more interesting, more relevant to hearing aids. Yeah, but that is true. But because of science requires everything, step by step to be validated. So,
and with lip sync, you are talking to syncing the target, like the other sentences, or is it more syncing the in these structures where you have all these different scenarios, more or less realistic characters.
No, well, we plan, in order to test the speech intelligibility, we want to use speech intelligibility tests, no? That there's also sentences, and yeah, the lip syncing is it's for the characters. They can say whatever they want. I mean, it's real time. You can have a microphone and speak, and they will move the lips. So
there's also another application to basically make live conversation through avatars. And so put people in different scenes and just make a live conversation, make it really closer to real life. But I think Joanna has a question.
I just wanted to ask about the OSA study, but now I already think I get it. So the thing is that you want to compare the intelligibility for OSA with video, OSA without video, OSA with, for example, video desynchronized, and so on.
yeah, I think it would be a very simple experiment. It's also audio only, and also with virtual characters. And then we have the video recordings, also with video recordings. Have 3 speech intelligibility rates, and then you check how much does it increase. It's not, I don't know, it's a simple study, but takes time to implement, write it down, blah, blah, blah. Yeah.
Then the next question, do you have an idea of how this goggle might disturb some cues that might be relevant for spatial perception, like reflections of the goggles or something?
Yeah, I thought about it that maybe because you're wearing this, then you have a different perception of the acoustics. But visual cues are so important. I think they just jump over all the things that you have. So, like maybe you have a different head-related transfer function, but you will first look at what you see rather than what you listen.
For example, in this demo where you have this radiating sphere, which you can circulate around your head. You have the impression that the sound is radiated from this sphere, although the Tasca system does not compensate for distance. Sorry?
Only the attenuation of the sound.
Only the attenuation, but not for the wavefronts and so on. So there is a lot of distortion already in the acoustic representation. Strong limitations in the realism of the acoustic representation, but if you really have the sphere in front of you and you move it yourself, this is just not so important. So this is also, we have to play with the limitations and make sure that whatever limitations we have in terms of the acoustics, that they do not influence basically the psychoacoustical result or the motion behavior. This is also what I need to show. So we are not checking back against complete physical accuracy, but against perceptual quality of the representation.
Yeah.
And at the beginning, you introduced that many become sick when they wear these goggles. And was this also already tested with elderly people? So these people who are more likely to be hearing impaired?
I know that age was not a factor for getting sick, I think. Like from these people that did 1,000 subjects, they check like the BMI, I think is the corporal weight and height index. Then they check the gender, they check the age. There were some minor effects, I think, on gender. The females would get sicker. But this could be because the goggles are designed for men faces, that they have maybe bigger faces with more separated eyes, and therefore women is smaller. And then age, maybe there was a slight factor for older people, but I don't remember that they said, yes, if you're older, you will get sicker on a like linear scale or exponential scale. It was when I did my studies, I had like it was not a Gaussian, the sickness. It was completely distributed over randomly. And I was getting people that said, I was asking if they play video games or they were used to watch TV very close, or if they got sick before in ships, if they usually get sick compared to other people. And I got people that I said, you're going to get sick, and they were played, like they were playing Counter-Strike, like looking on the corners when they were going with the game controller, and they were fine. They were like, yeah, perfect. And other people that were really slow, and they got really sick. Yeah.
What about Altscheid? Does the head-mounted display can correct for it, or can you
For?
when you are visually
Ah, okay.
Can you take off your glasses?
You can put the glasses on. I always use it with glasses. Yeah.
And another question regarding this lip change. Is it working on a phoneme basis or is it working on a word basis?
It's working on the spectral shape, and I'm checking for regions of phonemes where I'm supposed to be. It's a very simplistic strategy, okay? I did the lip sync. It was not part of the project. I wanted to have a character speaking. I spent 1 week like trying to solve it, and this came out. So if you look at the state of the art of this, it's much more far away. But if you want to check it out, there's a video online and there's a demo. All the videos that I've shown here, they are online demos. So if you have a computer, you can go on my webpage and check them out and try it out. So basically, it's you know that vowels, for example, they have different phonemes, formants, energies on different places, and then you can derive the mouth of the shape according to this, and then you have like a like a consonant. Your mouth will be closed, and then you can derive S, sh, f, that they have different high frequencies, and you can make this in real time because you just check the spectral shape, and then you say, okay, there are high energies and no low energies. It's a consonant like S, f, or v, and then you just make the mouth shape similar. But as you're switching so fast, and you can make also a smoothing function over this spectral shape, sometimes you don't see it that much. I mean, you saw on the first demo that there was a conversation. You don't look so much on the lip syncing. You might look it on a speech intelligibility test when there's a lot of noise, and you have to make a lot of effort to find it out. But when you have a conversation, maybe it doesn't take so much, the natural conversation without noise. Maybe you don't look so much for the cues of the lip sync. Yeah.
So maybe I should mention that the fact that in this audiovisual environments, the character has access to the clean signal always. That makes it much easier to do the lip sync.
Wouldn't it be even better if you have some kind of phoneme recognizer?
Then it wouldn't be in real time.
It's too long.
There's strategies that do this, and they basically, maybe they use Julius or HTK to do the phoneme recognition, which takes 20, 30 milliseconds, and then they have a prediction of what is the most probable phoneme that will come next according to the previous one and the language that you're speaking. But obviously this doesn't take a week to implement. This takes...
But we have experts on that.
Yeah.
I wonder if...
So there's other groups working on this for ages and very elaborate methods to do exactly this.
Yeah.
The future of this is in deep neural networks. This year in SIGGRAPH is the best conference on computer graphics. There were 3 papers on lip syncing with deep neural networks, and you had maybe virtual characters, but also videos that they would put an image of the mouth on top, and they had Obama speaking, and you couldn't see the difference from the video and from the synthesized video. So.
But this is basically batch processing. It goes back and forth across the signal and then to come up with the best.
I don't know. I think they work in real time. I think so. With deep neural networks, you can have direct mapping, maybe.
So if we, for example, if some from machine learning, some master student wanted to do this, it could be done. For our purposes, and also because we are more interested in that, we want to do this. But if some people from the speech department, recognizer people want to do it, why not?
But then you always.
We are not the experts.
Yeah, but we have the experts in-house.
But you always have to think how much time does it take to implement? Because when you use real video, you have to map the muscles of the face, and then you have to map this to the character. And in my case, we only have 3 movements of the mouth. That's like a key shape, opening the mouth and putting the lips inside. But if you have a video that you map all the movements of the mouth, then you have to have a virtual character that has the exact same movements, and it starts like adding complexity to the system.
I'm not talking of video recognition and trying to map the video listening to any character, rather automatic speech recognition technology applied to steer, so to say, the movement in a more elegant way than we do now by simple energy detection.
It's NeSSy and periodicity, so it's basically more the acoustical. That is the acoustical basis of what the speech people would also could be extended. So there's no, I don't see this being very easy. It's already including the acoustical features of what a speech is. And then it's mapped to the three nicely chosen blend shapes, which refer to the muscles most important to the mouth shape, which is like this, what you said, the more the smile and kiss and open.
Yeah.
Blends, right?
I mean,
how many blends do they use in these more elaborate systems?
There's 16 I've seen. That's the minimum I've seen, and then you can go up. I mean, people that do computer graphics in cinema, they use 1,000, 2,000. So we're using 3. I mean, it's relatively low effort to make 3. Yeah.
So we have a mapping between some LBC features plus periodicity on 3 of these blends. And this mapping is now not a network, it's a network, but of course we could replace this network by something that is better trained, for example. That could be done, it could be a master thesis or whatever, but it's not in the mainstream of what you are supposed to be doing, which is enriching basically hearing aid evaluation by visual input. But if somebody from the speech people want to work on it, why not?
Open project, yeah.
So you can provide them with the acoustic analysis you have and the blend shapes, and whatever they put in between, they can check.
Yeah. Yeah, it's a bit more work. But
well, I'm just thinking of the demos that I've seen so far. Well, the characters are a little bit grimly looking, and the mouse movements are okay. You see they are moving the mouse, but you don't see much of a relation between the acoustics and what they are.
Well, there's.
They're opening their mouth and so on, but at least I have questions. And so it may be that this little bit more extra effort you might the experts who are in the house you can look at that. You might improve that considerably. Not spending like master fees or so. Or not too much because that's outrageous, but just to
but for the purpose of what Gerard wants to do in this 3 years is this is sufficient, so
we have to check how much does it improve speech intelligibility, and then we can say, does it improve it? Yes? No? Then we know. You said it's not related. I think it's related. Somebody else saying, with this voice it's not related. Let's check it. Speech intelligibility, we get the result, we know. That's one of the things that we are doing wrong, that we don't have.
I'm not quite sure if we relate to the same image also.
Okay.
I'm just relating to the demo that was given to me 3 months ago or so.
It can be.
Comment on this. I think one demo which you have seen, it was a bug in task at the time, exactly that day you've seen the demo, which was some completely wrong timing of this mouse synchronization. Yeah. So there was probably one demo which was really failed. I mean, in general it's better than that. And the other point is, so until now we didn't have any audiovisual speech material, so there was no baseline to model and improve to something. So I'm pretty sure it would be easy to do, but of course it's always how much time would you like to invest. If there's anyone interested in doing this, we are very happy to support this and to integrate in our system.
So we will definitely validate the lip syncing system which we have right now, and we'll see an audiovisual benefit and compare it to what we find in literature at least. Maybe we also compare it to video, and then we say, okay, we get like 80% of the audiovisual benefit, or 60 or whatever. And then we say, okay, this is sufficient for the time being, and then we move on, and then as a side project, somebody can take it and improve it.
Still the question, how big is the benefit?
Yeah. This is what we have to check. This is why I said we have to do the validation, which we will.
And the maximum benefit that you can have, like the American studies, is in the order of 3 decibels.
Yes.
In single demonstration.
And we
then it's hard to measure that. And 3 decibels is not very easy to.
But we already know from Marty's study that we get some improvement by switching on the video. But there was, in that study, there was another complication, which is the uncertainty about what the speaker is. So if you normally measure audiovisual benefit, There's only one speaker, and you can exactly look at this. In multi-study, the subjects were to find out who is the speaker.
That was more the disambiguation. That was the
No, that is not true, because we compared to also video with only fish mouth. So they have the same possibility for disambiguation, but then yet when this lip syncing was not in fish mouth but the real one, there was an improvement. So we already have some indication of literature. And the improvement is not high, but in that case, basically, there was so much uncertainty about who the speaker was. I'm sure we did not measure the maximum possible benefit.
Also, until now, the main focus of our research was the behavior in the system, but not so much speech intelligibility. I think if going more into the direction of speech intelligibility, I agree that we need better models.
But for the time being, because we are looking more into movement, we only have to show, okay, the movement is realistic. We are not interested in really complete and
the head
movement behavior. We want to have this realistic, because this is what influences hearing aid function most. So this is why we are happy with the coarse lip sync so far. If it gives us some benefit, okay. Because for our purpose, this is a valid approach. But I agree, of course, if we are more, as Peter said, if we are more into really intelligibility, audiovisual speech intelligibility, this is not.
Okay. Somebody else? Florian? Yeah.
Two very technical questions. Do you include gazing direction, the simulation using pan-outer displays?
Gaze from?
Like eye gazing. Do you gaze to the left or to the right?
From the virtual characters or from the...
From yourself.
From yourself, if you modify the goggles? Yeah. No. Okay. Actually, there's a very interesting talk from, I think, Oculus Research, that they talk about this, because you're actually putting one image for each eye, right? And there's a claim that some of the sickness comes because the image that you see doesn't correspond to what your eyes see. And this is, I think it's called Bergen's accommodation conflict. And it's the same as when you're wearing glasses. When you have new glasses, if you're looking straight but you have a visual cue there, it will be very different when you take out the glasses, it will be in a different place. So it's the same with the goggles. And actually, in a previous study, I was adjusting the interpupillarity distance measure for the virtual camera on the virtual world, but you have to compensate for much more. Like also the distance that the lens is from your eyes, so you have a different nose and different shape, the lenses will be closer or far away. So in this study, before there was a tool that it was automatic to check this distance, but after seeing this conference, I don't know if it's, how much does it improve to change this or not? Because at the end, you're going to change the distance from the cameras, but then actually when you want to put the glasses, the cameras are going to be here, and it's going to be very different to check it from the eyes. So it's an open problem still with virtual reality. Actually also that people have different symmetries on the faces, so one might be here and the other here. Yeah.
The companies are working on that, because I think that's, I mean, many hearing aid manufacturers also work on steering something with eye-gazing directions on people, so that you don't necessarily point your head where you are listening to, but to the left and then gate, but still look at them. And that's something that's very unrealistic with these displays.
Because it's a very good point, because there's actually, I don't know, it's a very technical question. I don't know if to answer it now or, well, I can tell you that there's people working on this, that for example, there's a very important thing, the autofocus. So things that are far away and things that are closer, you will see them out of focus. And one strategy that they were doing is having one lens that would have objects that were in the virtual world at maybe 20, 30, 50 centimeters, they will be focused, but the rest blurred, and on the other eye would be otherwise. So actually we have really strategies on our system to do this. When you have an object that's closer, you would switch to the eye that sees better. When you have it farther away, you would switch to the eye that sees better on the end. And there's even a better technology that's called light fields, that basically you capture all the light coming from all the directions, and then you can modify it according to where you're seeing. So you could have gaze trackers. I think the Tobii, they already have gaze trackers on the head-mounted display, and then you could see where you're checking, and then rendering the image to be